AP and Honors Chemistry. This lesson is an extension of the concept of empirical formula, and you're going to learn really why do we use an empirical formula. What is it used for? So a hydrocarbon is a compound made of carbon and hydrogen. A combustion reaction burns a hydrocarbon with oxygen and produces carbon dioxide and water, and has a general formula that you see below. So there's a carbon-hydrogen compound with unknown subscripts at this point. Then you combust it, you light a match to it in an oxygen environment like the atmosphere, and you come out with carbon dioxide and water. So our goal is to determine the chemical formula, that is those X and Y subscripts for an unknown compound. Okay, so here's our example. Combustion of an unknown hydrocarbon produces 5.72 grams of CO2 and 1.17 grams of H2O. Determine the empirical formula of the compound. So, analysis. In the lab, we burned the unknown hydrocarbon in a combustion reaction and weighed the number of grams of each of the products, CO2 and water. How that's done is a topic for lab techniques. We won't talk about how those two compounds can be weighed, but we're just going to take it as a given that they can be. So in our world, we know that we obtained 5.72 grams of CO2 and 1.17 grams of H2O. All right, so we need to do a molar mass conversion. Okay, you're going to do this almost every day in this class, or quite a few times. So you're going to take those grams, and there's the equivalency for carbon dioxide. It's 1 mole CO2 equals 44.01 grams of CO2. You've seen that before. Same for water. 1 mole H2O is 18.02 grams of H2O. So we're going to use those equivalencies to convert to moles of carbon dioxide and moles of water, because chemical equations only work in moles. They don't work in grams. So our goal again is to determine the chemical formula subscripts for an unknown compound. There's the problem. So we're going to convert from grams to moles. So this is something you need to become proficient with. So we start with 5.72 grams of CO2. We use the molar mass. We put the grams on the bottom of the conversion factor, and that because we want grams to cancel out and we want moles of CO2. And when you do the math on that, you get 0.13 moles of CO2. So there's the mass. That's our world. That's something we weighed in the lab. There's the molar mass translator, and it gets us over to moles, 0.13 moles. Now we do the same for water, and there we go. Now we do the same for water. We have 1.17 grams of water. We use the equivalency for water to create two conversion factors. The one we want to use is the one with grams on the bottom also. So we're going to cancel, and we end up with moles of H2O. So now we have everything in moles. That means we can work in the chemical reaction. And for water, it's 0.065 moles of H2O. All right, so let's look at the flow of carbon. You'll notice carbon appears one place on the left and one place on the right. So we're going to take the carbon that we got on the right and work backwards to figure out how much carbon we started with in that unknown hydrocarbon compound. So there's 1 mole of carbon for every 1 mole of carbon dioxide. Be sure you understand that. You don't see the coefficient in front of C, and you don't see the subscript down below C, but that's a 1. There's an implied 1 there. Okay, and all of the carbon that we get from the CO2 had to come from the CH compound. There's no place else it could have come from. So again, our goal is determining the chemical formula for an unknown hydrocarbon compound. All right, so the next step. So here we go. Now down below, you're going to see the stoichiometric equation. In other words, the box to the end. Up above where it says pathway, it's going to show you the flow of the numbers. So it's the two different ways of looking at the same thing. So we're starting with 5.72 grams of CO2. And now we use the molar mass. We did this actually on the last step, and that would get us to moles of CO2. So in the pathway, we're going to end up with what we saw on the last slide, 0.13 moles of CO2. But we're not interested in CO2, we're interested in carbon. So what we see is that there's one, see the red ones appeared there in CO2? you have 1 mole of carbon for every 1 mole of CO2. So we're going to put that down in the stoichiometry below. 1 mole of carbon for every 1 mole of CO2. And then that's going to give us 0.13 moles of carbon. So in other words, our 0.13 moles of CO2 produces 0.13 moles of carbon. It's a 1-to-1 relationship. And where did all that carbon come from? The only place it could have come from is over here in the CH compound. So that means we know we have 0.13 moles of carbon there. So we're going to replace that X with the 0.13. So that's our subscript there. Now we're going to repeat, so study this, pause the video, study this, be sure you understand this flow. Now we're going to do the same thing for hydrogen. Okay, so we said we started with 1.17 grams of H2O. And there's the stoichiometry below and the pathway up above. So we're going to use the conversion factor 1 mole of H2O over 18.02 grams of H2O. And that's going to take us up here to 0.65 moles of H2O. Now we see that there's 2 moles of hydrogen in water. There's 2 moles of hydrogen for every 1 mole of H2O. Again, there's an implied 1 in front of the H2O. So you need 2 moles of water to create 1 mole of H2O. Okay, so there's 0.65 moles of H2O. And now you see in the stoichiometry below, it's 2 mole H for every 1 mole H2O, and that gives you 0.13 moles of H right there. Now, where did that H have to come from? There's only one place it could have come from, and that's from the hydrogen and the hydrocarbon compound. So we're going to place the Y with 0.13. So now you have subscripts, but you cannot have decimals or fractions as subscripts. They have to be whole numbers. So how do we get those to whole numbers, okay? Well, this is referred to, and get used to this phrase, a 1-to-1 relationship. If you have 0.13 moles of carbon for every 0.13 moles of hydrogen, that's called a 1-to-1 relationship. Okay, so what we're going to do is take those 0.13s, you put the biggest one on top and the smallest one on the bottom. Well, they're both the same number, so you just put one over the other. We must have integer values for the subscript of a chemical formula, so we convert the ratio below. 0.13, I could have put the carbon on top and the hydrogen on the bottom since they're the same number. That gives you a 1-to-1 relationship. So the empirical formula for this hydrocarbon is CH. Now, empirical formula of a compound is the lowest number ratio of elements. The molecular formula of a compound is the actual chemical formula of the compound. So I'm going to tell you right now, there is no such molecule or compound CH. It's simply saying that there's 1 C for every 1 H. So in the previous problem, we found an empirical formula for hydrocarbon compound, CH. But there's an infinite number of possible molecular formulas that could have that empirical formula. In other words, anything that reduces down to 1 carbon for every 1 hydrogen is a possibility. So it could be CH, it could be C2H2, it could be C3H3, C4H4, C5H5, and so on, okay? So there's an infinite number of possibilities. So what we need to do is find out which one is actually the molecular formula. All right, so how can we know what the actual molecular formula is if we know the empirical formula? Well, you need one more piece of information. The answer is, if we know the molar mass of the compound, we can derive the molecular formula of the compound from the empirical formula. Now you may say, how can you know a molar mass without knowing what the compound is? Don't you have to go to the periodic table and figure out how many atoms and how many what the mass is of each atom and multiply out like we've done before? The answer is no. There is a way to do it experimentally. We won't get into that now. Just accept that yes, there is a way to know the molar mass of a gas without knowing what the gas is. So example. It is determined that the molar mass of the CH compound from the previous problem is 78.11 grams. What is the true molecular formula of the compound? So note, we will leave the question of how molar mass of an unknown gas is determined for another discussion. We'll talk about that when we talk about lab techniques. Okay, so here we go. There's the problem. So we compute a scaling factor based on the ratio of the molar mass of the actual gas, what its true molar mass is, over the molar mass of the empirical formula. Now, what does that mean, molar mass of the empirical formula? So there's the ratio, molar mass of the actual molecule over the empirical formula molar mass. So we determine that the molar mass of the gas, the actual gas, is 78.11. So the empirical molar mass is simply computed by computing the molar mass of the empirical formula. So you have one carbon and one hydrogen. So that's 12.01 from the carbon obtained from your periodic table and 1.01 for the gas. You add those together and you get an empirical molar mass of 13.02 grams of CH. Okay, now what you do is you create a ratio of those two. 78.11, the actual molar mass, over 13.02, the empirical molar mass, and you get a scaling factor, which we just designate as N, of 6. So if the empirical formula is CH, we multiply those subscripts in the empirical formula, so it's C1H1 is really what CH means, by 6, and you end up with C6H6. So there's no such molecule as CH. But there is a molecule C6H6, and that's the molecular formula. Okay, let's do another example. So combustion of an unknown hydrocarbon produces 33.01 grams of CO2 and 13.51 grams of H2O. Okay, determine the empirical formula of the compound. So again, we have to do a molar mass conversion for those two. So we're going to do the same way we did it before. So carbon dioxide is 1 mole over 44.01 grams, and there's the pathway. It's starting with 33.01 grams. It's going to work its way up, and that, if you do the math on that, you get 0.75 moles of CO2. Again, we have 1 mole of carbon for every 1 mole of CO2, just like in the last problem. So that's a 1-to-1 relationship. That means we have 0.75 moles of carbon, same number of moles of CO2. So where did all that carbon have to come from? The only place it could have come from is from the carbon in the hydrocarbon, the CH compound on the left. So we're going to go ahead and replace that X with a 0.75. Okay, now we do the same thing for hydrogen. This is exactly the same as the previous problem, except the numbers are different. Okay, so we're going to start with 13.51 grams of H2O. And there's 1 mole of it. We need to convert that to moles, so we use the molar mass conversion, the conversion factor. We get 0.75 moles of H2O. Now there's 2 moles of hydrogen for every 1 mole of H2O. So that 0.75 is going to be multiplied by 2 to give you 1.5 moles of hydrogen. All of that hydrogen had to come from the CH compound. So there it is there. And so we're going to replace that subscript Y with 1.5 right there. Okay, now we have to get those to be whole number values. So what you're going to do is you're going to take the bigger of those two numbers and put it over the smaller. So there we go, 1.5 moles of hydrogen over 0.75 moles of carbon. So 1.5 over 0.75 is 2-to-1. So that means the empirical formula is CH2. All right, so now we're going to figure out what the actual molar mass of the actual molecule is. It could be that. There could be a CH2 molecule. We don't know that yet, okay? But we see that the actual molar mass obtained by a laboratory experiment is 28.06 grams of this compound. And then down below, we compute the empirical molar mass, which is 1 carbon, 12.01, 2 hydrogen, 2 times 1.01, that gives you 14.03. So that's the empirical molar mass, the molar mass of the empirical formula. All right, so there we go. We put the 28.06, the experimentally determined molar mass of the actual molecule, over the empirical molar mass, which is 14.03, and we get a conversion or a factor, scaling factor of 2, n equals 2. So that means we take the empirical formula and we multiply the subscript of C by 2 and the subscript of H by 2, and what that gives us is C2H4. That's an actual molecule. There's no CH2 molecule, there is a C2H4 molecule. All right, and that takes care of this lesson. It's a little bit involved. It's going to take some practice, so I'll be sure to give you plenty of practice on this.